Thank you, folks. Really easy going up here, so it's very interactive as far as I'm concerned when I'm doing my presentation. So questions, comments pop up. Don't wait for a break. Just go ahead and raise your hand or yell it on out. I'm here to answer questions right on the spot. They seem to get forgotten if they don't get asked right away, so feel free to yell them out when you got them, okay? Quick background on myself. I got about 27, 28 years in the lead-acid battery business from all aspects of it. Distribution, delivery, warehousing, pulling, picking, placking, charging, testing. A little bit of engineering background with some of the guys at the plant that have spent a lot of time with me. My comment to Jeremy when Jeremy was done, I take the kind of expertise and the technical expertise that a guy like Jeremy has, and I dumb it down for a dumbass like myself to regurgitate to everybody else so that we're all on the same page when it's said and done. So I am not the engineering type that Jeremy is, but we pride ourselves at Crown Battery on technical knowledge as well to give that out because we believe that information is power when it comes to the product. Whereas Jeremy was talking a lot about the lead acid product, the chemistry and everything else that goes with it itself. My presentation is going to be more geared towards the proper care, proper maintenance of that product once it goes into the application. With lead acid product in particular, pretty much across all the various types of lead acid batteries in the marketplace today, there is some type of maintenance that is required, whether that be a proper charging algorithm, whether that be proper watering care, and several other factors that go with that. The most important aspect of after the quality of the product and you've chosen the product correctly, then what is the care that we're providing for that battery? Because once that battery has all three of those things put together, you've got something that's of value at that point. And what we're trying to establish with product in the marketplace, lead acid as a general term is that in terms of cost per ampere hour, cost per watt hour, whatever equation you want to apply to a lead acid product, we feel probably has the best value still in the aftermarket today or in the OE side as well, regardless of what you're seeing from these alternative chemistries that are coming down the road, such as lithium, lithium iron phosphate, salt water technology, the rest of that stuff that goes with it. And just my 2 cents for those alternative technologies is this. As Jeremy mentioned more than a few times, lead acid's been around for almost 150, 160 years now. We know the ins and outs of lead acid technology and what it does and what it can't do. We also know the features and benefits of the product as well. So with that base of knowledge that we've acquired over that 150, 160 years, we really can optimize your purchase for you when it comes to a lead acid product and really give you the right product that you need for your specific application, and then set very specific expectation levels for that product that you can expect to achieve out of that product in terms of the amount of power it produces or the amount of time it'll last in the application once you get in there, okay? Okay. So before I get into I want to give you another look at the chemical process that Jeremy was talking about earlier on. And the only reason I'm going to do that is because this is more of my personal understanding of what I see happening inside of a lead acid battery when that product is actually producing power. Who in the room has heard of the term acid transfer before? Only because you were in Fremont, Ohio yesterday or last week. Okay, so acid transfer is another terminology, another phrase that occurs within the electrical chemical process of the battery as the battery is producing electricity. If you take, in my area of expertise that I deal with a lot of deep cycle flooded batteries, okay, 6-volt golf cart batteries, for example. If I was to have a 6-volt golf cart battery sitting up on the table up here, I chop the top of the battery off and I look down into it, what am I going to see? Plates? What do those plates consist of? Basically 2 primary ingredients. Sorry? Lead actually makes up the two of the primary ingredients, but there's specific terminology for the specific types of lead that make up the finished plate. What's the base structure of the plate that holds all the material together? Grid. And then what's applied to the grid? Active material, lead oxide, paste, called a couple of different things, okay? We'll call it lead oxide for all intents and purposes here. Jeremy talked a little bit about the calcium versus the antimonial aspects of a lead acid battery, right, with the plate structure. Primarily that structure, that ingredient with calcium and antimony is utilized in the grid structure of the plate. Lead, as Jeremy mentioned more than a couple times, lead is so soft and pliable by itself that from day one, when lead acid batteries were first being produced, manufacturers had to add an ingredient or an alloy to the lead to provide tensile strength for that grid. And the ingredient basically from day one was antimony, which was a great alloy to blend with the lead, which provided tensile strength for the grid structure, but then also applied for a real good free flow of electrons back to the grid metal itself as the energy was passing into and out of the battery. One of the byproducts of antimony, though, is that when the battery was on charge, the battery gassed. So who today remembers back in the 60s, 70s, and 80s, maybe even early 80s, that as part of the PM service when a car came in for an oil change, part of the problem was you popped the caps on the battery and you checked the fluid level in the battery, right? Because back in those days, everything, both starter and deep cycle, utilized an antimonial alloy. In the late 70s, early 80s, and manufacturers began to experiment with other alloys to add to the lead grid to provide tensile strength, but wouldn't cause the battery to gas. And that ingredient they all pretty much settled on back in the early 80s was calcium. And that's when Delco, for example, first came out with that flat top sealed battery. That was your first basically maintenance-free product at that point used in a calcium alloy. So those are your two primary structure differences between the grid, between maintenanceable and non-maintenance, and the fact that antimonial is going to require some maintenance, the calcium product typically will not. What else is going to be in those cells of that 6-volt golf cart battery when you cut the top off and look down into it? Fluid.
Yeah.
We call it electrolyte. What's the electrolyte made up of? Sulfuric acid and water, distilled water. What else?
Strap.
Top strap going across the top of the batteries. You've also got the separator material between the positive and negative plates so that the batteries don't touch. But for the purposes that we want to talk about here, these are your two primary ingredients that the battery utilizes to produce electricity within itself, okay? So utilizing this same 6-volt golf cart battery as an example, let's just touch base briefly on the acid transfer process and what goes on from our standpoint with that in a deep cycle application, for example, of a golf cart, okay? So you got a guy in a golf cart, first tee, hits the tee shot, jumps into his golf cart, mashes the gas pedal, and the cart goes down the road. Why? When the guy hits the gas pedal on the golf cart, the electrical motor applies a draw to the battery bank to get the electric motor pushing the cart down the road. That electrical draw begins the process of acid transfer where the plates within the battery begin to attract the sulfuric acid out of the electrolyte solution. And as that sulfuric acid is bonding with the material on the plate, the positive plate, because the positive plate is the one that does all the work within the battery, that chemical reaction results in electricity being produced within that plate. Electricity comes up out of the plate through the grid metal, up through the top strap, and out the terminal to power the load coming off the battery at that point. Okay? That process continues until one of two things occurs. Either the positive plate exhausts the supply of sulfuric acid that's available in the electrolyte solution, or the amount of the active material has taken on all the sulfuric acid that it can take on, and at that point the battery is dead or low voltage at that point. My company, for example, when they make this electrolyte solution, utilizes an electrolyte solution that measured with the hydrometer comes in at 1.265. Jeremy talked a little bit about what specific gravity means. Baseline from a water standpoint, distilled water is 1.000. We mix sulfuric acid with that distilled water to come up with a heavier solution that measures 1.265 as our base recipe. If the battery is in a discharged state, and then based on the concept of acid transfer, if you were to measure the specific gravity of the cells at that point with a hydrometer, what would you think you would see versus the 1.265? It'd be lower than 1.265. How low? Depends on how deeply discharged the battery is. Okay? That process then reverses itself when an outside charge current is putting current back into the battery banks, reverses the process of acid transfer, and we know that the battery is fully charged when? when we returned all the sulfuric acid from the positive plate to remix with the electrolyte solution, and we're back to our base recipe of 1.265 specific gravity. Okay? Every lead acid battery in the marketplace today, whether it's AGM, whether it's wet flooded, whether it's my manufacturer, whether it's Northstar, Trojan, or whomever, we're all beholden to this process of acid transfer, okay? So as a manufacturer, we try to come up with ways to best allow our batteries to resist the wear process of acid transfer, while at the same time producing the most amount of power out of that particular product, realizing that those two things are mutually exclusive. As a manufacturer, I can actually boost my capacity with the exact same layout of a battery by making my electrolyte hotter by using a higher concentration of sulfuric acid. But what's going to be my byproduct of that? Life. Because I'm going to have a hotter acid, I'm going to have more corrosive environment inside of the battery. The battery's going to wear out faster. So as lead acid battery manufacturers, we're trying to walk that fine line of providing the most amount of energy density within this specific case size that we have to deal with, while also getting the longest amount of life out of that product at the same time. Okay? And going back to the comment is that everything that we do from a maintenance standpoint with the product in terms of charging and watering that goes with it is all contingent upon this process. And if you go back to this as your base recipe of what's going on inside of the battery, this will help you with the troubleshooting aspect and trying to find the proper product for the proper application. Questions or comments on this real quick?
So when you go down to Napa and buy the electrolyte, put it in your battery, you're shortening the life instead of just putting distilled water in it?
If the battery has been operated in a proper environment through the time that you've been doing that, yes, you are going to be shortening the life of the battery. There are cases where if the battery was spilled, for example, and you needed to add a certain amount of true electrolyte back to the battery to have the proper concentration of acid in there, sometimes we say yes, sometimes we say no. We just don't know because how much electrolyte really spilled out of the battery. But if the battery is operating in a proper environment through its cycle life, the only thing that needs to be added back to the water is just distilled water. Any other questions or comments? All right, let's cover some of the easy stuff real first here. So one of the things that we try to start off with is safety. So batteries have a couple things going on with them we've got to be concerned about from a safety standpoint. Sulfuric acid, which is in the electrolyte, you have to watch out for. We highly recommend that when you're around a wet flooded product and maybe as well as AGM products as well, you got some safety goggles on over the top of your eyes, okay? It's an explosive mixture of oxygen and hydrogen. When the battery's on charge, the battery is gassing 2 molecules of hydrogen to 1 molecule of oxygen, which is, that has to go back into the battery somewhere down the road for a wet flooded product. But in a gaseous state, 2 molecules of hydrogen and 1 molecule of oxygen is an explosive mixture. So if you guys have a battery bank that's on charge, for example, you need to check those batteries out when they come off of charge, shut the charger down, don't disconnect the leads right away, give it 10, 15, 20 minutes for the gas to dissipate, and then do your disconnects on the battery charger at that point so you don't have an explosive issue or an explosive event as you get an arc while you're trying to disconnect one of the leads on the charger, for example. Okay? Electricity is voltage, don't need to talk about that too much, we know exactly what that can do. And then batteries are heavy. Use your legs when you're picking the damn things up. When you got a 185-pound AD, that's no fun doing that by yourself, so grab some help at the same time and have somebody else move that battery around with you when you guys are putting them in the vehicles, okay? Safety glasses, goggles, or a face shield, rubber gloves, boots, and or an apron. One of the things that we do recommend, I'm assuming everybody here has the eye wash stations on hand in facilities now, right? We have to cover that. So if you guys are covering the basics here, we definitely force it. This is something that we do in our own facilities as well, dealing with batteries or lead acid batteries, and OSHA and EPA will be happy to do so as well. Okay, some technical references really quick. Voltage is electrical pressure, measured in volts, forces the current from the battery through the load, and then also forces the current back into the battery on the recharge side as well. Jeremy did a really good job of touching on that, so I don't think we need to mess around with that too much. Current is the electrical charge or capacity measured in amps that the voltage is pushing into the battery during the recharge cycle, or the battery is being pulled out of the battery during the discharge cycle. about some things that we might not have covered earlier then. So ampere hour. Ampere hour is a measurement that measures the total amount of energy stored in a battery. If I've got a 6-volt, 220 ampere hour battery, what does the 220 tell me?
How long it'll produce it?
One more time, sorry?
220 minutes.
Nope, not that one.
How many amps do you have for an hour?
So this battery, for example, there's a few things you have to understand about what this number is based upon, and it is based upon a timeline draw or a constant draw coming off of the battery to get to this specific number. In the world that I play in and the world that you guys typically play in with ampere hours when it comes to deep cycle batteries, the measurement or the unit of measure that we typically look at this battery is known as C20, which is basically known as also the 20-hour rate, okay? Somewhere on the spec sheet, if you guys are looking at a battery, you should be able to find this terminology. If you can't, typically speaking, the industry defaults to the 20-hour rate, and you can use that as your baseline to base the rest of the criteria on. So once we know what the constant is of this particular number that it's based upon, then we can actually determine what this number really means. So 220 ampere hour at a 20-hour rate, you take the 220 and divide it by the 20, and you come up with 11. What is that 11?
How long a battery will last at a certain amount of draw?
So the 11 is the draw. A 220 amp hour battery at the 20-hour rate will produce 11 amps continuous for 20 hours. Before the battery drops below 1.75 volts per cell. Which is 100% depth of discharge. At 75F. So for all the electrical applications that you have out there, I'm sure that the motors or whatever the other draws are have a rating of what they draw in terms of amperage. So once you've got that off the faceplate of the device or the application that you're looking at, you can then size the battery bank accordingly to make sure that you've got the right battery fitted in the right application. Okay?
What does the C refer to?
Constant.
Oh,
So constant for 20 hours is basically what it boils down to, okay? And how we get to that number again is we take that C20 number, divide it into the amp hour capacity of the battery to come up with our draw coming off the battery at that point. Jeremy mentioned a couple of times that a fully charged battery, well, flooded lead acid, I should say, is 2.1 volts per cell, which equates to about 12.6 volts for a 12-volt battery, right? 2.1 times 6. 1.75 volts per cell is 100% depth of discharge. There's no more energy left in the battery at that point. I'm just curious, because one of the things I run into all the time is that the person who has this 12-volt battery, if I take 1.75 and divide it by the 6 cells, I come up with about 10.5 volts. Well, 10.5 volts for a 12-volt battery doesn't sound all that discharged, right? Right? So if I've got a customer that's coming in and says, hey, I've got a battery, it's discharged, but it's not all that bad at 8.0 volts. How bad is it? It's really bad. And then the confusion, I guess, what I'm trying to point out here is that the customer who comes in, or the user, I should say, the end user who thinks that a 12-volt or a 6-volt battery fully discharged is 0 volts is way off the reservation. And these are things that we've got to overcome to some extent. The bottom line is that in the 12-volt battery, the reason that 10.5 volts is 100% depth of discharge is why? There's not enough pressure left in the battery and were to force current out at that point. So anything below 10.5 volts is really doing damage to the battery over a very short period of time. Okay, questions or comments on this?
So you concentrate, your molecular weight of your acid, is that going to be affecting your voltage?
Well, absolutely, because as the battery's being discharged further and further, where's your sulfuric acid migrating to? Into the plate, leaving behind.
So your acid weight is going to affect your 2.16 slightly?
Absolutely correct, yeah. The hotter the acid that you're going to utilize for your electrolyte-based solution, the little bit higher voltage you're going to get for the overall nominal voltage of the battery. Direct correlation.
And so what are the manufacturers, what's the difference in the different manufacturers of that voltage if they're adjusting the weights?
Depending on the type of chemistry that they're utilizing, whether it be an AGM pure lead product or a traditional antimony or wet flooded product, manufacturers have determined on their own which is the better recipe for them to utilize for their own electrolyte. I will tell you that in the wet flooded world, 1.265 is predominant across most of the industry, by far. There might be one or two guys out there that vary slightly from that, but 1.265 is the majority of it. Okay. Questions or comments on this? Freezing. When Jeremy mentioned the freezing of a battery. When you have a fully charged battery, lead acid product, okay, and your gravity levels are 1.265, for example, for the wet flooded, the freezing temperature of electrolyte at that molecular weight is about 70 degrees below 0 Fahrenheit. So when you've got a fully charged battery, unless you're on the north slope of Alaska or other parts like that, you're not going to have a freezing issue with the battery. What do you think the primary problem comes from when it comes to a battery actually freezing? Why does a battery freeze? Batteries sit in a discharged environment, in a colder environment, and as the more battery is the discharge, the higher the freezing temperature is for the product at that point. I live in Michigan. We have an issue with boating season, very compressed of about 3.5 to 4 months worth of boating, which really sucks for me because I love to boat. But what we do is that we try to tell our customers there's a maintenance aspect you have to provide for that product once the boat's pulled out of the water in the fall to be stored for the winter. And if nothing else, make sure the battery is fully charged, confirmed with the hydrometer before the boat's pulled out of the water, and then disconnect one of the leads and let it sit. Worst case is your discharge rate is going to be a lot slower because the colder temperature is slowing down the self-discharge rate of the battery. Other than having to boost the battery come springtime, you should be okay.
What about sulfating the battery? They'll tell you if you let it sit too long.
We're going to cover that here coming up in the next couple slides for sure. Okay. Other important aspect for you guys, I bet you're jealous you didn't see the whiteboard up here, Jeremy, right? Deep cycle batteries are measured in ampere hours. What are starting batteries measured in for capacity? Cranking amps, right? Or cold cranking amps. Cold cranking amps equals what? The amount of amps that a battery can deliver for 30 seconds at 0 degrees Fahrenheit before falling to what voltage level you think? 1.75 volts per cell per amp. So once you've got the base figured out for what that measurement's rated upon, you guys can actually then buy the correct batteries for the applications those batteries are going to be going into. As an example, the firefighters in Phoenix, Arizona, right? Do we really need a high-end 1100 or 1500 cold cranking amp wet flooded battery in Phoenix, Arizona for that fire truck these days? And in fact, in a lot of cases, the product might be acid starved because there's too much lead plate, not enough electrolyte for that type of a heated environment. So there's some things and some deduction and some investigation that has to go on when you're purchasing the product to go into specific applications, because depending on where you're at, what the application's utilizing, and the product that's going into it, it's gonna change your tune a little bit of what needs to be utilized. Who's heard of cranking amps before? Same exact thing? It's just the measurements taken at 32 degrees Fahrenheit versus 0 degrees Fahrenheit. Why do you think this came about? Why the migration, or why the dual use of CCA and CAs now in applications for cranking applications? Yeah, exactly right. It's the marketing guys, for example, that were in Phoenix, Arizona, where the customer walked into an AutoZone in Phoenix and said, hey, listen, I really want that 1000 cold cranking amp Group 34 battery, which has a whole bunch of lead plate and not a lot of electrolyte. And when it's 115 degrees in Phoenix, Arizona, it's 165 degrees under the hood of the car, and that stuff's evaporating. So by going to a 32 degree Fahrenheit rating, now they take that 800 cold cranking amp, which becomes 1000, number looks good to the customer, right, when it's all said and done, buys actually the proper battery by mistake. A little bit of misleading marketing that's actually doing the customer a favor. Okay. Reserve capacity, I've got the answer up on the board. I'm gonna go real quick with this one. RC, or reserve capacity, is a rating in time, minutes, that the battery either has a 25 amp draw, a 56 amp draw, or a 75 amp draw applied to it. Stays above 1.75 volts per cell at 75 degrees Fahrenheit. So again, talking about what we've got is a couple of mutually exclusive things over here, where ampere hour and reserve capacity is all about providing a steady stream of power over a longer period of time, versus the cold cranking amp and the cranking amp ratings that provide quick bursts of power to get the starter spinning and get the vehicle up and running. The best option is to try to find the best of both worlds, or if you know specifically what the battery is going to go into at that point, buy the best product for the best application.
So I don't recall the 75 amp, the 25 or the 75 or the 56 number.
Great question. I'm sorry, I should have clarified that. So the reason for the 3 different draws is that the 25 amp rate is basically applied to everything that's commercial heavy-duty starter battery and smaller. So like your Group 31, full state of charge, because of the result of the chemical process with acid transfer of not purging the sulfuric acid from the positive plate. It is absolutely critical.
So the best thing for us to do if we have storage batteries, ensure they're charged fully,
Yep.
and then they'll store for.
What's the best way to confirm that the battery is at a full state of charge though? When you have maintenance to the cells, when you have access to the cells.
Hydrometer.
Hydrometer by far. Because if you get back to the 1.265 number that is most of the lead acid world's base recipe for electrolyte, we know what?
It's fully charged.
We've purged the residual sulfuric acid from the plate to remix with the electrolyte solution to get back to our base recipe of 1.265.
Do you have a preference between the hydrometer and the refractometer for checking specific?
Either one's fine, man. And we're big school. Again, Jeremy and I are 2 different guys. He builds a sealed maintenance-free product. I build primarily a wet flooded product that requires maintenance. Because of my product being accessible with the cells, either one of those 2 is perfectly fine and our preference of choice when it comes to checking those types of batteries by far. The cool thing about the hydrometer, the refractometer, is that at any time during the state of charge process, when the battery's being discharged or when the battery's being recharged, you get an instant snapshot of what the state of charge of the battery is at that time when you're checking with the hydrometer or refractometer. If you were to check it with a voltmeter, for example, what are you going to pick up for a battery that's been on charge for 5 or 6 hours? You're going to see surface charge, where you probably still have some sulfuric acid trapped within the positive plate that hasn't been returned to the electrolyte, and you're going to have kind of a false reading when it's all said and done, right? The hydrometer doesn't lie, or the refractometer as well. Okay. Questions or comments on sulfation? Okay. Who's heard of stratification before? Okay? Stratification is basically, the electrolyte is made up of what? Sulfuric acid and water. So if a lead acid battery, a flooded lead acid battery, is allowed to sit for an extended period of time, and or the battery is not being returned to a full state of charge after each recharge cycle, a process known as stratification begins to occur within the electrolyte solution. And basically what that is that the electrolyte begins to separate. The sulfuric acid, because it's heavier, falls to the bottom of the cell, where you have a much higher concentration of acid at the bottom portion of the plate, which is much more corrosive than it should be, and you've got water on top. And if that happens over a period of time, stratification leads directly to then sulfation within the positive plate, and then that sulfation begins to work its way up the plate, just like in its other characteristics, which reduces capacity of the battery to the point where it's not going to work anymore. Okay? Stratification is addressed through a couple different charging methods, which I'm going to cover here in a second. But the bottom line from our standpoint as a lead acid deep cycle producer, I can tell you that 90% of all premature failures in lead acid deep cycle products flooded result from sulfation within the plate. Okay? If you're going to err on the side of anything when it comes to a lead acid deep cycle battery, err on the side of overcharging the battery, believe it or not, because if you don't get the battery back to a full state of charge, sulfation is going to occur and the battery is going to fail. What would be a byproduct of what you would have to do if you're going to overcharge the battery though? You got to check the water more frequently because you're going to be using a little bit more fluid within the battery when it's all said and done. Questions or comments on sulfation or stratification?
How long does it take for sulfation to start? So scenarios, if you're run it down and then you're trying to charge it back up, it's in a boat and you can't get it back to full charge before you have to go back on your battery power, and you do that for like 2 weeks.
So sulfation and how quickly it spreads is in direct correlation to how deeply the battery is discharged and how long it's allowed to remain in that state. So it's time and condition of the battery at that point. If a battery is at 100% depth of discharge, sulfation begins to occur within days, literally. At 50% depth of discharge, you're probably looking at weeks. Lead acid batteries, by definition, even when they're sitting on a shelf, self-discharge. And you can get to a point over a period of time where that lead acid battery that has not been installed into any application whatsoever has discharged to the point where sulfation is beginning to work its way up the plate. Okay? Much slower process on self-discharge, but the more deeply the battery is discharged, the more quickly sulfation will begin to spread.
So as a rule of thumb, when you have a bank of batteries stored and you don't charge it on, the interstate guy comes in every so often, you put a sticker on it or you replace it with one with a sticker, what's a good rule of thumb? How long can you leave them before you need to worry about that battery? And the one that they put the stickers on, to give them a different date,
Yep.
how good are they?
So what's he, I guess the first question I would have is what's he doing to the batteries that he's putting a new sticker on? Is he actually charging those batteries
That's what
first?
they say, they think
Okay.
they take them back to charge.
So if they're charging them, that's a good thing then, and there's no problem with that whatsoever. So basically, there's 2 shelf life parameters to deal with when it comes to lead acid batteries. Actually, there's more than that now because of AGM and all the rest of the stuff as well, but from a wet flooded standpoint, deep cycle or antimonial deep cycle batteries have a shelf life in this climate of probably somewhere around 4 to 6 months max. And then calcium wet flooded batteries probably have a shelf life approaching 1 year in this climate. But realize that temperature on lead acid batteries affects it like any other chemical reaction. The hotter the temperature, the faster the chemical reaction is going to run, which is going to discharge the battery faster. The colder the temperature, the slower the discharge rate will be. So in Phoenix, Arizona, where I have a pretty large distributor, for example, of my deep cycle products, his shelf life in high summer is literally 60 days. And he's got to boost the batteries on the deep cycle product. On the calcium starter stuff, in that climate in the summertime, he's probably somewhere around 6 to 7 months. Jeremy, AGM?
First of all, I just wanted to mention shelf life that he's talking about, and correct me if I'm wrong, Chip, but is down to 50% state of charge.
Correct, that is correct. Yeah, it's not flat dead.
Right, not flat dead, it's 50% state of charge. AGM product, again, handles much longer. If you're on AGM product at 77 degrees Fahrenheit, which is fairly warm, much warmer than you guys sit at, it will still go 25 to 26 months before 50%. So that's not a concern. And sulfation is a real concern for every battery chemistry, not just chips batteries. Every battery sulfation, because that crystallization is very difficult. Now, you brought up carbon batteries earlier. Carbon actually, because of the additive, actually reduces the amount and has spacers, so it doesn't happen as quickly. Also, some manufacturers will add tin and selenium into the grids to allow for the electrons to get to more parts of the grid, to allow for the breakage of those molecular bonds that happen. So Chips Company, Northstar, all the manufacturers are constantly trying to find new ways. As he said, sulfation kills batteries. It's probably the leading killer of all batteries, not just his. And manufacturers are constantly trying to find ways to improve it.
The adage, the old adage that because we deal with such a cyclic environment with our product is that batteries don't die, they're murdered. In the way that they can be murdered, they're murdered in a whole wide variety of applications and ways, right? Think about a starter battery, for example, in that environment versus a deep cycle battery in its environment. The starter battery world is actually, other than first responders, you guys have it tough because of all the various things that are on the truck to go with the battery, but just think about a normal over-the-road car, right, passenger car. Once the battery provides crank to the starter and the charging system takes over, the battery in that environment is fairly benign, right? The charging system has the battery on a float charge. Most, if not all, the electrical draw is being powered from the charging system on the vehicle, and the battery's in a pretty happy environment of around 14.5 to 15 volts. Optimum, right? In the deep cycle world, it's not the case. In the deep cycle world, everything that that is needed to power that duty cycle, whether it's scissor lifts going up and down, whether it's a golf cart going down the golf cart path, whether it's a renewable energy system at night, everything in that duty cycle comes from the battery. How many different things can affect the battery at that point? Everything. Temperature, how deeply it's being discharged, the variance rates and recharge rates, it all just becomes a big nightmare equation and one try to figure out where root cause actually lies. So we're very cognizant of the fact that sulfation is the #1 killer of batteries, but we also want to realize that we want to figure out how the batteries are actually going to be used so we can set the proper expectation level for that product once it's installed. Questions or comments? Dan, you had something you want to say?
Well, he caught me on the same question on the shelf, what do you mean by shelf life?
Yep, good. Okay.
So as far as like purchasing batteries for different companies, one thing I like about Interstate is that they can come and check your batteries.
Correct.
If you buy batteries from other people and have them sitting on the shelf, then you're kind of assuming that responsibility of maintaining those.
So the way I kind of look at that is that you got 3 points on a triangle, right? You've got price, the quality of the product, and then the support or service of that product. And then those 3 things together make the value when it's all said and done. This is not a selling session, so I'm not going to get into what Interstate does versus what Crown does versus what Northstar does. You need to do your research to figure out how that battery's built, what you're going to pay for it, and then what you're going to be expected to perform on that product before it goes into the application. And when you put all 3 of those pieces of the pie together, then you guys can figure out what the value is for your each specific location at that point. And that's something that we really try to do with our customers, both from the dealer distributor side as well as the actual end users, is that you guys above anybody else in this industry when it comes to lead acid batteries are not a part number and price buyer, right? You don't want the cheapest price Group 31 just because you're paying the cheapest price for a Group 31. There's a whole bunch of other things you guys are looking at before you actually make that purchase of that product. And we try to do the same thing as well. Okay. So, definition of a cycle. Now we're talking cyclic applications here, or deep cycle storage. Charging, the cooling period after the charge cycle is depleted, after the recharge cycle is terminated, the battery is allowed to rest or cool back off again before the next discharge cycle occurs. Causes of failure of batteries in cyclic or deep cycle applications are over discharge, overcharge, overwatering, or underwatering. In other words, everything that can affect the deep cycle battery can kill it when it's all said. In our world that we play in today, over discharge is by far the #1 reason for premature failure in deep cycle lead acid batteries, okay? And think about over discharge from a standpoint of is that when the battery's being taken beyond its parameters, then what does that do to the recharge cycle on the backside to get the battery back up to a full state of charge? Expensive. Is there enough time for it? Is there enough horsepower to get it done? And if the battery then doesn't get back to a full state of charge, what's happening inside of the positive plates within the battery at that point? Sulfation, because you're not purging the sulfuric acid from the positive plate completely. So in the world that we play in, we try to make sure that deep cycle batteries are married to the appropriate recharge cycle or recharge device, because if we don't have that to go with a high-end, high-quality product, we're not going to have a high-end, high-quality product anymore. So it's important you look at all aspects of it when it's all said and done. Over discharge obviously then leads to undercharge on the backside, because if you're taking the battery past its parameters and you don't have enough time or horsepower within the charger to get the battery back up to a full state of charge, the battery's going to continuously operate below full charge and kind of work its way down over a period of time. Okay. Basic charging facts. Never plug or unplug a battery from a charger while it's running. Why? Sparks, battery's gassing when the battery's on charge. The battery is gassing, hydrogen and oxygen. Any kind of spark from disconnecting it from the charger while it's running, for example, can lead to an explosive event. Okay? Never allow a battery to sit in a fully discharged condition. Why? Positive plate is retaining all the sulfuric acid. It speeds up the process of sulfation, leads to undercapacity of the battery or premature failure. Never add water to cells before charging unless the electrolyte level is